Hello learners, welcome to this video lecture on the Otto cycle of hair-standard cycles presented by myself, Ranjit PK, Assistant Professor, Department of Mechanical Engineering, Global Academy of Technology. In this video lecture, you are going to understand how the Otto cycle functions. Then we are going to look at the derivation, both two derivations, expression for efficiency in terms of the compression ratio and expression for mean effective pressure and a few sample numericals. So let's begin learning. Otto cycle is an ideal cycle for the spark ignition engines or the petrol engines. It essentially consists of four internally reversible processes: isentropic compression, that is process 1 to 2, then constant volume or isochoric heat addition, process 2 to 3, then isentropic expansion, process 3 to 4, and isochoric heat rejection, process 4 to 1. So let us put our focus on understanding how the cycle functions. What happens is when the air fuel mixture is compressed, it is taken as an isentropic compression. So the piston moves from the bottom dead center to the top dead center and the pressure increases and the volume reduces. So this is shown by the process 1 to 2 on the PV and the TS diagram. So there the isentropic compression of the air fuel mixture occurs. In the next process 2 to 3, there is an external heat addition, or essentially in the actual cycle the spark plug initiates the spark and it gives the source, the heat source, and the air fuel mixture, the compressed air fuel mixture ignites, whereas thermodynamically it is represented by a heat addition process 2 to 3. It is an isochoric heat addition where the volume of the air fuel mixture remains the same. In the process 3 to 4, what happens is the air fuel mixture ignites, the piston moves from top dead center to bottom dead center, and then it starts to liberate its heat energy. So this is shown in the process 3 to 4, that is nothing but the isentropic expansion, the piston moving from the top dead center to the bottom dead center as isentropic expansion. And in the fourth, in the last set of process, that is the constant volume or the isochoric heat rejection, the exhaust gases are let out into the atmosphere. These exhaust gases also contain some amount of heat, hence it is approximated as a heat rejection process shown as an isochoric heat rejection process 4 to 1. So you essentially see the top dead center and the bottom dead center marked along with this. So this is at the bottom dead center and the piston is at the top dead center here. At state point 3, both the pressure and the temperature is found to be maximum in the cycle. Now you might observe here that it is shown as air only and not air and fuel mixture. So when we analyze this cycle or the working of this cycle thermodynamically, we have made some assumptions. What are these assumptions? The gas in the cylinder is a perfect gas, that is, it obeys all the gas laws and the specific heat is taken to be constant. And the second assumption is all the processes in the cycle are reversible in nature and it is internally reversible, basically isentropic in nature. The cycle is considered to be closed with same air remaining in the cylinder. This is very important. Whereas in the actual cycle, what happens is there is fresh air fuel mixture taken or sucked into the cylinder. But to analyze this thermodynamically, we have considered that it is a closed system and it is only air that is taken as the working fluid, hence the name air standard cycle. So this air circulates back in the system again. The compression and expansion processes are adiabatic and with zero internal friction, that is, these are isentropic in nature, and the combustion process is replaced by a heat addition process from an external source. So what we have assumed here is the combustion process, instead of being produced from the spark plug, is taken as a external heat addition. So there is an external source, that is what we have assumed, and this external source provides the required amount of heat to the system. Similarly, the exhaust process is replaced by a heat rejection process, and this ensures that the working fluid is returned to its original condition. So even for the exhaust process, it is a heat rejection process, and this exhaust process has its working fluid retained to its original state point. So it is at state point 1. With these assumptions, we now look at how do we derive the efficiency of the Otto cycle in terms of the compression ratio. It is a usual practice to list down the assumptions, that is these 6 assumptions, when we start deriving the expression for the Otto cycle. We consider 1 kg of air undergoing the cycle of operation. The heat supplied is in the process 2 to 3, that is the isochoric heat addition. So we have the heat supplied equation as Cv into T3 minus T2. Similarly, the heat rejected, the isochoric heat rejection process is 4 to 1. So the heat rejected is Cv into T4 minus T1. The work done or the net work done is written in terms of heat supplied and heat rejected, that is W is equal to Q in minus Q out. So we have written this expression, we have substituted Q in and Q out, and a small simplification here. So Cv being common factor in both Q in and Q out is taken as the common factor. The efficiency is written in terms of net work done by the heat supplied. So we have substituted the equation of net work done and heat supplied. We have both the Cv both in numerator and denominator. So we simplify this and we obtain an intermediate equation for the efficiency in terms of temperatures. So we have all the 4 temperatures, and this intermediate expression, let us call it equation number 1. Now, if we look at process 1 to 2, if we write the governing equation for this isentropic process, T2 by T1 is written as V1 by V2 power gamma minus 1. So this forms the governing equation which relates the temperature and the volume for an isentropic expression. Similarly, for the process T3 to 4, it is an isentropic expansion. So you have T3 by T4 is equal to V4 by V3 power gamma minus 1. So if we have a close look at the PV diagram, we have already observed that process 2 to 3 and process 4 to 1 are isochoric in nature. So V2 equals to V3 and V4 equals to V1. This is the observation that we can infer. So if that is the case, T3 by T4 is already known, the governing equation T3 by T4 is equal to V4 by V3 power gamma minus 1. So V4 is equal to V1 and V3 is equal to V2. So we have for these expressions T2 by T1 is equal to T3 by T4. Since the right hand side of these expressions are the same, we are able to equate this expression. A small rearrangement is what we have done here. T3 by T2 is equal to T4 by T1. Then we subtract 1 from both the sides and we have a rearrangement. So we obtain T4 minus T1 divided by T3 minus T2 as T1 by T2. And we know T1 by T2 also as V2 by V1 power gamma minus 1. So the intermediate expression for the efficiency which we had was this, that is efficiency is equal to 1 minus T4 minus T1 divided by T3 minus T2. That is written in terms of T1 by T2 and in turn written in terms of the volume. So what we have done here is the intermediate expression for the efficiency is written, which was originally in terms of the temperature, is now written in terms of the ratios of volumes, that is V1 and V2. Let us call the RC as the ratios of volumes, that is volume at the beginning of compression divided by volume at the end of compression, that is V1 by V2. V1 is the volume at the beginning of compression, V2 is the volume at the end of compression. That is nothing but total volume by swept volume. So we have Vs plus Vc as the total volume, which is equal to V1 divided by the swept volume, that is nothing but the V2. So we can write this expression of the efficiency in terms of the compression ratio, that is nothing but efficiency is equal to 1 minus 1 divided by Rc power gamma minus 1. A quick look at the expression for efficiency. tells us that the efficiency of the ideal Otto cycle depends on two factors. One, the compression ratio RC, and second, gamma, the specific heat ratio of the working fluid. So, essentially, the efficiency increases when both the compression ratio and or the specific heat ratio is increased. So, as we increase gamma, the efficiency increases. As we increase RC, the efficiency also tends to increase. Now, the next part is also looking at the derivation of the mean effective pressure. Before we move on to looking at the derivation, we'll understand what is mean effective pressure. It is a fictitious pressure that, if acts on the piston during the entire power stroke, would produce the same amount of work as that produced during the actual cycle. So what this means is, when the piston is moving from either TDC to BDC or BDC to TDC, it is a fictitious pressure. The pressure keeps on changing. We have observed this from the PV diagram. So as the net work is achieved in this cycle, we take one average fictitious pressure which is equal to the pressure of the entire power stroke. Whatever the power stroke was executed, whatever the pressure with which the power stroke was executed, and which would produce the same amount of net work. So, W net is written as mean effective pressure MEP into piston area into the stroke, or this piston area into stroke is nothing but the displacement volume. So, mean effective pressure is rearranged as net work done divided by the displacement volume, which is nothing but V1 minus V2. Now, how is this mean effective pressure useful? This is used basically as a parameter to compare the performance of the reciprocating engines of equal sizes. So, we compare the mean effective pressure that is achieved for various reciprocating engines, and we fix this as one of the performance comparison parameter. So, the engine with the larger mean effective pressure delivers more net work per cycle and thus is said to be performing better. So, as the mean effective pressure increases, the area under the PV diagram increases. Once the area under the PV diagram increases, the net work done automatically increases. So, this is a mean effective pressure. The net work done is written in terms of all the four processes occurring in the cycle: P3V3 minus P4V4 divided by gamma minus 1 minus of P2V2 minus P1V1 divided by gamma minus 1. Now, what we do is we write the process for 1 to 2, process 1 to 2 and process 3 to 4. We write this pressure, the governing equation, in terms of pressure, which is nothing but RC power gamma, where RC is the compression ratio V1 by V2, and similarly P3 by P2 is taken as pressure ratio, that is again equal to P2 by P1. So if V1 by V2 is equal to RC, implies V1 is equal to RC times V2, and similarly V4 is equal to RC into V3, because V1 equals to V4 and V2 equals to V3 from the PV diagram. Therefore, the net work done expression is written or rearranged as 1 divided by gamma minus 1. We take P4V4 as common here. So, it is P3V3 by P4V4 minus 1. And in this side, we take P1V1 as common factor, P2V2 by P1V1 minus 1. So, W net is further simplified as V3 by V4 written as 1 divided by RC, and V2 by V1 written as 1 divided by RC again. So, this is further simplified. The P3 by P4 into RC minus 1 is further simplified as RC power gamma minus 1 minus 1. How did we write this? Because P3 by P4 is equal to RC power gamma. Similarly, P2 by P1 is equal to RC power gamma. We have P3 by P4 here. It is RC power gamma divided by RC, which is nothing but RC power gamma minus 1. Similarly here, P2 by P1, that is nothing but RC power gamma. RC power gamma by RC power RC is RC power gamma minus 1 minus 1. And we have V4 is equal to V1, so we have taken V1 as the common factor. Now, Again, in this expression, Rc power gamma minus 1 is a common factor. So we have Rc power gamma minus 1 into P4 minus P1, and we take P1 as the common factor here again. P4 by P1 is equal to Rp, pressure ratio. So we have W net written in terms of P1 V1 divided by gamma minus 1 into Rc power gamma minus 1 into Rp minus 1. The next step, what we do is we substitute this mean effective pressure in the earlier expression of mean effective pressure is equal to net work done divided by V1 minus V2. So far we have simplified and rearranged the net work done equation that is substituted here. Now the numerator is going to remain the same. The denominator is where we simplify. V1 minus V2 is written as V1 minus V1 by Rc. How is this? Because Rc is equal to V1 minus V2. Then V1 into 1 minus 1 by Rc is written as Rc minus 1 by Rc. We have both V1 in the numerator and the denominator. So the final expression for the mean effective pressure is written as P1 Rc into Rc power gamma minus 1 into Rp minus 1 divided by gamma minus 1 into Rc minus 1. This Rc is written in the numerator. Okay. So this is the final expression for mean effective pressure. However, we do not use this very often for solving the numericals. What we do is we use the net work done in terms of heat supplied and rejected, and we take this displacement volume as pi d square by 4 into L, and that is how we end up calculating the mean effective pressure. So before we move on to the numericals, what are the set of instructions that we need to look at? We need to write the given data very clearly, and by default please write the PV diagram without fail, so it helps the reader understand from where is the process starting, because many of the textbooks or many of the students or many of the authors who are writing PV diagram, they do not always start the isentropic compression process as 1 to 2, and the state point 1 starts from a different set. So this PV diagram helps the reader understand what is the state points that is taken. Then always ensure that the units of temperature are in Kelvin only. Please write the relevant formula and show the substitution compulsorily, and make a habit of highlighting the correct final answer. Some of the questions may need some comment sometimes, so accordingly this has to be written. This is basically a summary of the slide containing all the relevant formulas that are used to solve the numericals. This is a very useful slide. Maybe you can make a note of this in your notebook when you practice, and then you can start solving the numericals. If you like the content, please consider subscribing to the channel and hit the bell icon so that you get the further updates on the video. We look at the sample numericals. First numerical being an engine running an Otto cycle has an efficiency of 60% and gamma is equal to 1.5. What is the compression ratio? So here they have given the Otto cycle efficiency, they have given the value of gamma. What is the compression ratio? We need to find what is the compression ratio, that is nothing but RC. Step number 1, write the given data. Efficiency is 60% or 0.6, gamma as 1.5. Then step 2, write the relevant formula. Efficiency is 1 minus 1 divided by Rc power gamma minus 1. We have efficiency, we have value of gamma, we need to find Rc. So after substituting the relevant units, you end up getting Rc, the compression ratio, as 6.25. The second numerical, an engine working on an Otto cycle is supplied with air at 0.1 megapascal and 35 degrees Celsius. The compression ratio is 8. The heat supplied is 2100 kilojoules per kg. Calculate the maximum pressure and the temperature of the cycle efficiency and the mean effective pressure. Take Cp is equal to 1.005 kilojoules per kg Kelvin, R as 0.287 kilojoule per kg Kelvin, and Cv is equal to 0.718 kilojoule per kg Kelvin. Now, We look at what is given. An engine working on an Otto cycle is supplied with air at this particular temperature and pressure, or particular pressure and temperature. So P1 is 0.1 megapascal, T1 is 35 degrees Celsius. The compression ratio RC is 8. The heat supplied Q in is 2100 kilojoules per kg, and then Cp, R and Cv are given. We need to calculate the maximum pressure and temperature, which is nothing but P3 and T3. Find the cycle efficiency and also the mean effective pressure. So from here onwards, we start writing the PV diagram with the state points. The given data, T1 is 35 degrees Celsius, converted into Kelvin is 308 Kelvin, RC as 8, Qin is 2100 kilojoules per kg, then P1 0.1 megapascal or 100 kilonewton per meter square, CV, Cp and R values written. And from this value, given value of Cp and Cv, we can find the gamma, that is the ratio of adiabatic index or specific heat ratio. So it is 1.4. Now we have the expression for efficiency. Efficiency is equal to 1 minus 1 divided by Rc power gamma minus 1. So it is a fairly simple substitution. We already have the value of Rc, we have the value of gamma, we end up finding the efficiency. So it is 0.565 or 56.5%. Next, we look at the process 1 by 2. T2 by T1 is equal to V1 by V2 power gamma minus 1, which is nothing but Rc power gamma minus 1. So Rc is 8. That is what is substituted here. So we have T2 as 708 Kelvin. Then Q in is equal to Cv into T3 minus T2 is the formula. The heat supplied, that is Q in, is already given. So after substituting the relevant numbers, we end up calculating T3. So T3 is 3633 Kelvin. Then T2 by T1 is also equal to P2 by P1 power gamma minus 1 by gamma. That is nothing but finding the value of P2. So we have T2, T1, P1 gamma values. We end up finding P2. So P2 takes the value of 1.87 megapascal. Further, for the process 2 to 3, T3 by T2 is equal to P3 by P2. So we end up calculating P3, which is 9.42 megapascal. So the maximum pressure is 9.42 megapascal and the maximum temperature is T3, 3633 Kelvin. Now, in order to find the mean effective pressure, what we do is we first find the W net. The generic expression for the efficiency is net work done divided by heat supplied. So we have the efficiency, we have the net heat supplied. We can find the net work done as 1186.5 kilojoules per kg. So mean effective pressure is W net divided by V1 minus V2. We end up calculating V1 as R T1 by P1. So it is generally PV is equal to MRT is the generic expression because it is the ideal gas law. M is taken as 1 kg or on a kilo mass basis. So V1 R T1 by P1. It should be noted that for this expression only the P has to be in kilonewton per meter square only. I repeat, P has to be in kilonewton per meter square only and R as kilojoules per kg Kelvin. So we end up getting V1 as 0.884 meter cube per kg. Then RC is equal to V1 by V2. We have already the value of RC and V1. We can end up calculating V2, which is 0.11 meter cube per kg. So we end up calculating the mean effective pressure by substituting its values of W net, V1 and V2. We get mean effective pressure as 1533 kilopascal. The next numerical. An engine of bore 250 mm and stroke 375 mm works on Otto cycle. The clearance volume is 0.00263 meter cube. The initial pressure and temperature are 1 bar and 50 degrees Celsius. If the maximum pressure is limited to 25 bar, find the air standard efficiency of the cycle and the mean effective pressure of the cycle. So here they have given the bore, which is usually denoted as small diameter, that is the diameter small d, and stroke, the piston length it traverses in a single cycle, that is capital L, and the clearance volume Vc is given, initial pressure and temperature, so P1, T1 is given. The maximum pressure is limited to 25 bar. This is nothing but P3. Okay, we need to find the efficiency and the mean effective pressure. So the first step, write the PV diagram, then the given data. D as 250 mm in terms of meter SI units, we write it as 2.25 meter. Similarly, L stroke length 375 mm as 0.375 meter. Then Vc, that is 0.00263 meter cube. T1 50 degrees Celsius when converted to Kelvin is 323 Kelvin. P1 is 1 bar and P3 is 25 bar. So RC is equal to V1 by V2 or Vs plus Vc by Vc. What we do is we calculate the swept volume given as pi d square by 4 into L. So when we substitute the values, we get Vs, the swept volume, as 0.184 meter cube. So we end up calculating RC because Vc is already given. We have calculated Vs. We get the compression ratio as 8. Then once we know the compression ratio, it is easier to find the efficiency. 1 minus 1 divided by RC power gamma minus 1. Since the numerical said assume ideal conditions, we are going to take gamma as 1.5 or 1.4, any value. So we get efficiency as 0.565 or 56.5%. Next, the pressure ratio is P3 by P2 or P4 by P1. Then for the process 1 to 2, we write P2 by P1 in terms of the volumes RC power gamma. So we end up calculating P2 18.3 bar. Then the pressure ratio 1.36. Here we have used the generic expression that we have derived to find the mean effective pressure. So substituting all the units, we have the mean effective pressure as 1.334 bar. Next, numerical. In a constant volume Otto cycle, the pressure at the end of compression is 15 times that at the start, with the temperature of air at the beginning of compression being 38 degrees Celsius. The maximum temperature attained in the cycle is 1950 degrees Celsius. We need to evaluate the compression ratio, the efficiency and the net work done. Take gamma as 1.4. The pressure at the end of compression is 15 times at the start, which means what is the pressure at the end of compression? We take 1 to 2 as isentropic compression. The pressure at the end of compression, so which is P2, is equal to 15 times at the start. So is equal to 15 times of P1 with the temperature of the air at beginning of compression, that is T1. Then the maximum temperature is nothing but T3. So these are the given values. So we write the we write the PV diagram of the Otto cycle. Then the given data P2 by P1 is equal to 15. T1 is 38 degrees Celsius, that is 311 Kelvin. Then T3 as 1950 degrees Celsius, that is 2223 Kelvin, and gamma as 1.4. So P2 by P1 is equal to RC power gamma. RC is what is to be found, which is nothing but 6.9. So once we know RC, we end up calculating the efficiency. We get 0.538 or 53.8%. So T2 by T1 is equal to RC power gamma minus 1. We end up calculating T2, that is 671.7 Kelvin. Then further, similarly T3 by T4 is equal to RC power gamma minus 1. We end up calculating T4, 1029 Kelvin. Then the W net is CV into T3 minus T2 minus of T4 minus T1. We have all the values. When we substitute, we get W net as 597.5 kilojoules per kg. With this, we have completed a few sample numericals and the derivation of the expression for efficiency and the mean effective pressure. Thank you.